Okay, welcome to section guide sheet number 4, refraction of light. We're going to start with objective 4.4.4, describe waves in 2 dimensions, including the concept of wavefronts and rays. We usually think of waves, like when we make them on a spring, as being just up and down on a piece of paper. But in reality, waves are multidimensional. A wave front is one like position on a wave. So here the wave fronts have all been drawn as the crests of the wave. If you were to look downward at this, you would see those crests as a series of linear motions. And then the gap between two of those lines would then be the wavelength. Now we do and often do and can turn that wave front into more of a single line, and we call that a ray. So if I take and draw an arrow down the center of the wave front perpendicular to the wave front, then that arrow segment is usually called a light ray. Usually it's used with light, but it could be used with any wave. It's called a ray. It allows us to more easily measure angles and other things. So the black picture here, the color in black, that's a light ray. And then the ones in red are wave fronts. So wave fronts, one after another, and light ray. Okay. Now here's a picture of a ripple tank where you're generating waves just by pushing on a bar, and notice those are the wave fronts there. And again, if we wanted to turn that into a ray, we would make a line perpendicular to it, something like that. Okay, now look at refraction. And refraction is the changing of direction of a wave as it passes between two different materials. A simple one-word synonym for refraction would be bend. To bend, to change direction. Refraction occurs when light crosses the boundary between one material and another. The main factor is speed. Light is a very good example. Light moves fastest in a vacuum. If it moves from that vacuum into some other material, it's going to slow down. And when it slows down, if it's approaching the surface at an angle, then there's going to have to be a change of direction. Now, to track that change of direction, there are multiple things. There's another portion, another idea that's full of different terminology. I'm going to label these various things on the picture here. The boundary would be B here. So we're going from air up here in this area to water down here in this area. The normal, which is a very important reference line, it's not an actual physical thing, but it's a 90-degree line to the boundary. The incident ray, incident coming into the light. So here's a light ray. Notice it's an arrow, and it's coming into the air-water boundary. The refracted ray, so refraction is what occurs once you've hit the boundary. So the refracted ray is the ray after you've gone into the new material. Now we always measure our angles with respect to the normal. So theta I is the incident angle of incidence, and theta R is the angle of refraction. There are 2 different media in this particular case. There's air, through which light travels very well, and there's water, through which it slows down significantly. Medium is simply the stuff, the matter in between. So the stuff the wave moves through. Mechanical waves have to have a medium. Electromagnetic waves like light do not need a medium. They can travel through empty space. So in fact, light and all the electromagnetic waves tend to be slowed down by more dense media. The refraction will take place right here at the interface between the light ray hits the new boundary, and there's going to be a bending situation. Okay, in this next one, you want to draw a normal line. So you want to draw a line, and you usually would normal lines, we like to make them some kind of dash. And normal simply means perpendicular to the surface. So you're going to try to draw it 90 degrees to the interaction where the ray meets the surface. Then you're going to want to measure the angles between the normal and the incident ray. So that would be, this would be theta I. And then between the normal and the refracted ray, and that's going to be theta R. So theta I, theta R, theta I, theta R. And you would simply use a protractor. It would be the easiest way. Just place it down there and measure those angles. If you do so, these are the approximate angles you should get. 40 goes down to 20, 30 goes up to 60, and 55 goes down to 40. Again, I can't stress enough that it must be the angle from the media, from the normal, not from the surface. It's not this angle. It's not this angle. It has to be measured with the normal to make the relationships of refraction work. Should notice in the first one, the angle got smaller. That indicates, it tells us something about the two media. In the second one, the angle got larger. That also tells us a different thing about the two media. We'll see that as we move along. Okay, as light passes from one medium to another, as it changes speed, it's going to refract. Now, there's only one condition under which the light won't refract at a boundary of two different media, and that's if it hits the surface at 90 degrees. If it hits at 90 degrees, perpendicular to the surface, so here's the boundary. If the light ray comes straight in at 90 degrees, then it's along the normal, and it's not going to change position from the normal. It's going to go straight in, and then it's going to go straight out. So that's the only condition under which it will go straight through two different materials. Okay, now this next part will help us figure out the direction at which it's going to bend, whether it'll bend toward the normal or away from the normal. Optical density is the property that we say whether it slows it down more or less. Light always travels slower in media with greater optical density. It's harder for the light to get through. Every material that can allow light through, transparent materials, will have its own unique index of refraction, the symbol for which will be n, lowercase n. That tells us the relative speed. Light will travel slowest in media with higher index of refraction. So c is the speed of light in a vacuum, 3 times 10 to the 8th meters per second. If we have an n, n's always going to be a number between 1 and higher, so therefore as the n gets larger, being that it's in the denominator, then our velocity is going to become less. Some common materials and their index of refraction: water 1.33, ice just a little bit less, glass 1.50, and diamond 2.42. We can go ahead and use this relationship to calculate the v, the speed of light, in those different materials. Again, it has to be less than c, 3 times 10 to the 8th. So for the first one, we would take 3 times 10 to the 8th and divide by 1.33. And that'll give us the speed of light. So try those for yourselves, but these are the values you should get. 2.26 times 10 to the 8th meters per second. For water, a little bit faster than ice because it's a little lower index of refraction. Even slower in glass, has a larger index of refraction. Now, there are many types of glass, so different types of glass will have different index of refraction, but they'll be around 1.5. Diamond, one of the reasons diamonds sparkle so much is they have this very high index of refraction. Notice glass and diamond are very different, so no matter how much you try to make a good looking diamond out of glass, it'll never look the same as a diamond because of that index of refraction difference. Now, which way is it going to refract? As the light travels from a medium in which it moves faster, it travels into a medium in which it moves faster, then what you should expect to happen is, if I'm coming in at this angle, that's the ray, here's the wave front. Now, we're going to go faster over here after we go into the new material. That means this part of the wavefront right here is actually going to speed up. Now, if we're moving along in a series of lines and this side of the line gets faster, then the whole line, in order to keep together, is going to have to change direction, something like this. And that means that when we go from slower to faster, SFA, slower to faster, we're going to bend away from the normal. So it's going to be away when you go from into a material where it travels faster, and then towards when you go into a material where it travels slower. So if we travel slower, then what you're going to find is angle coming in, raise there, there's the wavefront. Now this part again is going to hit the new material first, but it's going to cause it to slow down. That's going to mean this side is going to actually speed up, causing the wave to tilt something like this, which is toward the normal. So in terms of optical density, when you go into a medium that's more optically dense, you're going to slow down, so you're going to move towards the normal. And then when you move into a material that's less optically dense, you're going to speed up, so you're going to go away from the normal. So that would be answer A. So slower to faster, away from the normal, faster to slower, we're going to move toward the normal. Okay, so we have a number of diagrams here. In which case is the light bending toward the normal? Circle all that apply. Diagram A has gotten a little messed up in my picture, so we're going to let that one go. But diagram B, so here's the normal. This angle is larger than this angle, so this is away from the normal. Here's the normal. This angle is larger than the new angle, so this one is bending toward. Again, this picture's no good, but here the incident angle is much less, so this one's bending away. Okay, so we're going to wrap this up by looking at the last, this picture over here. Now I've marked out the various angles, and there are 3 media, creating 2 boundaries. Light must travel in medium 1, it goes from a larger angle to a smaller angle, so that means it's going faster to slower when it goes from 1 to 2, so therefore it must travel faster in medium 1 compared to medium 2. And then when you look from 2 to 3, the angle is getting larger, so that means it has to be going from a slower to a faster media. So that means it must travel slower in medium 2 than it does in medium 3. So as long as you can figure out the direction of the change of angle, you can figure out if it's faster or slower. There is also a relationship known as Snell's law, which will allow us to actually measure that change. Okay, that's it for this portion. We'll wrap it up in the next video.